Okay, so again, from where we left off, we were finding the moment of inertia about the centroid of 1, right? And then we were shifting it by this distance, this purple distance right here at the top. And so that distance, we said it was going to be 16 minus another 2. Sorry, not 16. Whatever 20 is right here, minus what? Well, we got to do minus 2 and then minus another 11.862. And so we did, that's what we did here. We did 18 because 20 minus 2 is 18 minus another 11.8462. And that's going to give us our moment of inertia for the top shape about the z-axis, which is the neutral axis. And so we did answer this question. The location of the neutral axis, that is y equals to 11.8462 millimeters. And that's the neutral axis with respect to only bending. Now the total, we don't know. The total, we don't know. So now what we're going to do is we're going to do I2. And what is I2 going to be? And I'm trying to track everything to make sure that we're doing things correctly. I2 is going to be 1 over 12 because it's the same shape. It's still a rectangle. But then we're going to have the base, which is 4 millimeters right here. And then we're going to have the height, which is 20 minus 4, so that's 16 millimeters cubed. And then we want to shift that. Now this, we want to shift it by this other amount that I depicted earlier, by this amount right here. So how are we going to do that? Well, that's basically our distance y because we assumed we were starting from this datum right here, see? So let's just put that in there. And what is that going to be? Well, let me just make clear though. I made a mistake here. We're looking at the centroid here. So the centroid would be here. So we're actually looking at this distance right here. So to find that distance, then that's going to be wherever the centroid is minus, subtracted to the y that we found. So we know that this is halfway, so this is 8 millimeters. And so really what we have to do is we have to say 11.8462 millimeters minus whatever the point for the centroid is, and all of that is squared. Now that's the distance. I like to put the distance after the area. So what is going to be the area for this? Well, it's going to be the base, which is 4 times 16. So we'll put that over here, 4 times 16 millimeters squared, right? And so now, what are we going to get for these two numbers and the one at, oh, we already did the one at the top. Okay, well, I'm going to input this into the calculator. So 10 over 12 times 4 to the third plus 40 times 18 minus 11.8462, all of that squared. And so that's going to be 1,568. 1,568 millimeters to the fourth. 1,568 millimeters to the fourth. Now, let's do the same thing for the bottom. So we're going to get 4 divided by 12 right here. 4 divided by 12 times 16 to the third plus 4 times 16 times 11.8462 minus 8, all of that squared. And what we get there is 2.3, or I can just say 2312 millimeters to the fourth. So now the total moment of inertia is going to be the sum of the two. And I can add them up because now they're with respect to the same axis of rotation, namely z, which is what the moment is applied about. And so we have 1,568 millimeters to the fourth plus 2,312 millimeters to the fourth. So that's going to be 1,568 plus 2,312, and that's going to be 3,880 millimeters to the fourth. And now that we have that, I already mentioned that D now we can find because we know that this distance right here is 50 millimeters. That comes from the graph right here. And then we know that this distance to the neutral axis, that distance is what? It is, now we have to find it. Now be careful, we have to find it from the top to here. We have it from the bottom to there. So if we do it from the top, it's going to be 20 minus 11.8462. So it's going to be, so D is going to be 50 millimeters plus 20 millimeters minus 11.8462 millimeters. And so once we have that, what are we going to get? Well, we're going to get 50 plus 20 minus 11.8462. I'm just inputting into the calculator. I get 58.15 millimeters. And now we can use our formula. So the stress about the x-axis, because it's going to be a distribution kind of like this, is going to be equal to what? Well, it's going to be equal to the internal load over the area, the total area of the cross-section, plus the moment that the cross-section is subject to, and actually there's a minus, the y, which is the distance from the centroid where the moment is applied, divided by, sorry, not where the moment is applied, the distance from the centroid where the force is applied. So in this case, ours is D, right? Because this is our force, this is a reaction moment, and it's caused by this force at this distance from the neutral axis. All right? And now we divide everything by the total moment of inertia about that neutral axis. So let's put everything in. The P is going to be 400 newtons. Was it newtons or kilo newtons? Okay. The area is going to be the sum of these two areas. So 40 millimeters squared plus 64, which is going to be 104 millimeters squared. I don't know why I wrote to the fourth here. I apologize if that confused you in the previous video. And then we're going to subtract. What are we going to subtract? My M is going to be a moment. And we can actually find the moment. So let's do that first. So going from this one, we know this has to be 0. So the moment has to be the negative of whatever this 400 times that distance is. So that's 400 newtons times 58.15 millimeters. And so that's going to be minus 400 times 58.15. That's going to be minus 2326, minus 23260, 23260. And this is going to be newtons times millimeters. And this comes from the fact that we found D. So I should probably rearrange this because I don't want this to confuse you. So this should go over here. And we did this. We did this after finding D. So I can put D right here. And so now we have this whole expression right here where we can put negative 23260 newtons times millimeters. And then all of that is going to be multiplied by the y. And the y is going to be what? Well, my y is going to be that distance, right? The moment is applied at a distance given by this right here. Because we want to know the stress at point A and D, where is A is at the top, A is right here, D is at the bottom. So from the top, how distant are we? Well, we're going to be the whole 20 minus wherever the neutral axis is, which we said is 11.8462. So that's going to be what? That's going to be 20 millimeters minus wherever the neutral axis is, which is 11.8462. 11.84, that 11.8462 millimeters. I'll give myself a little bit more space here. And then we're going to divide this by I, which we calculated to be 3,880 millimeters to the fourth, right? So the units work out. And now we just want to plug everything in and see what we get. So let's see. We're going to get 400 divided by 104 plus, because the minus cancel out, another fraction. At the top, we're going to get 23260 times 20 minus 11.8462 divided by 3880. And what we get is 52.73. 52.73. And now we have millimeters, newtons over millimeters squared, which is megapascals, which would be newtons over meters squared. So that's why we didn't convert them. And now we need to specify that it's in tension because we got a positive value, right? So let's see over here. Does that make sense that the top is in tension? Well, it's going to be bending like this, right? Because I'm pushing here, I got something like that. And so it's gonna wanna move that way. So yeah, that makes sense. So that's tension, and we wanna put a parenthesis in there for tension. All right, so let me ask you another question. Now let's find point D. Well, to find point D, we have basically the same formula. So this is point A. For the sigma x at point D, what we really want to do is we want to change the y. So we're going to have the same values here. We're going to have 400 newtons over 104 millimeters here. And then minus, we're going to have that same moment, because that's not changing. The location where we're measuring the stress is changing. Now, what's the distance from the neutral axis to the point D? Well, that's exactly what we calculated when we found the position of the centroid, because we started from the bottom, right? And so it's going to be 11.8462. 11.8462 millimeters. Now, be careful here because you're going down, so it's going to be in the negative direction. And then we're going to have the same I. So right here. And now what are we going to do? Now we're going to put it into the calculator. So we got, I'm going to try and speed it up by copying what I wrote before, changing what I have inside. And what we get is negative 67.2. 67.2 megapascals. Now the negative means we're in compression, which makes sense with our intuition. Okay, so this was how to do it. I think there's a lot of room for error, and I think that's why it's kind of important to keep your things straight and to practice to do it fast, because in the GR you're not going to have time to reason things through. You're just going to have to be very, very fast. I hope this was useful, and that was it for this problem 4115.